Walk into the typical undergraduate chemistry laboratory and what do you see? The students are working away at the lab procedure while the instructor sits in a corner grading papers. Sure, the instructor is available to answer questions and monitor lab safety, but doing precious little in the way of teaching. Why not use that time for one-on-one teaching, the best kind of teaching that can be tailored to the individual student, focusing on the techniques, observations, or calculations that have caused students the most trouble in previous years. The first time I tried this, I think it was around 2002, I walked up to students chosen at random and started asking questions. Is the reaction product a solid or a gas? What gas do you think it is? How could you figure that out? Big mistake. About 2/3 of the students responded with,
"Why are you picking on me? You're not asking anybody else to answer those questions."
The key is to build this interaction into the structure of the assignment, to make it an expectation. Here's how I do it. Explain something or other to the instructor is right there in the laboratory instructions, in boldface italics so students can't miss it. Get my red check mark there or suffer the consequences, a loss of half a point on your grade for the lab. When the full course grade is based on 630 possible points, half a point is absolutely trivial. Doesn't matter. Compliance is universal and nobody complains. In fact, my student evaluations show that this is one of the most popular things I do. Here's an example, an experiment heavy on physical chemistry. Students use the Clausius-Clapeyron equation to calculate the enthalpy of vaporization of water. At the freshman level, you're lucky if students can substitute their measurements into the equations correctly and not mess up the calculations. To expect them to understand what they did and why they did it seems too much to ask. But that's what I'm trying to coax out of them in this exercise. First, I ask them for 2 reasons why the air bubble in an inverted graduated cylinder immersed in water gets bigger as you heat the water. Students explain as they are watching it happen in the apparatus they have assembled. Gas is pushing the water out.
Because it's so much gas, the pressure of the gas is...
Yeah, but what's causing so much gas?
With the fact that the vapor pressure is increasing.
Vapor pressure is increasing, and what's the other reason there's so much gas?
Because the water's trapped.
Well, that would be the vapor pressure
Oh,
of
because
water.
it's trapped. It's trapped inside
Well, that
the...
is trapped.
The gas is trapped inside the thing and it can't go out.
No. So what happens when you heat gases?
They expand.
They expand. PV equals nRT.
Right. But
Yeah.
since it can't go anywhere,
It just has to make the bubble bigger. That's right. Okay. So the water vaporizes and the air expands. Later we draw on this explanation, for which the student has already received a red check, to understand why the calculations are structured the way that they are. Here, crushed ice has been added to the apparatus to lower the temperature of the bubble to near 0 degrees Celsius. Why is it important to measure this volume so accurately?
But after we're done with this, then we only have air. So in order to
Why is that?
Because all the water is condensed because it's submerged in such a low temperature.
Okay, so the vapor pressure is really low at this temperature.
So in order to find the amount of water we have to subtract the initial volume from the volume now, which contains only air.
Okay, so these volumes are both air and water, and we want just the water vapor.
Yes.
Yes, okay. That was a very good student, so the explanation was completed quickly. This also happens when the student rehearses the answer with the student lab aide, who is trained to guide students without giving away the answers. I encourage this process since this is formative rather than summative assessment. That is, it's about learning, not about grading. The discussion always ends with a red check mark, but it usually takes longer. Here's a student who needed some guidance.
By doing that step, then we found out that the vapor pressure inside there, that's what it would be when it was cooled down and it doesn't change. So you use that in your equation in order to find the different types of pressure. And then for the equations, you use that to find, I use that to find the pressure of air and then the pressure of water. And that would affect the pressure of water because that's kind of the to like the most pressure or the lowest pressure.
Okay, so what's the objective of this part of the lab? What are we trying to calculate?
Change in enthalpy.
Right. And what are we graphing in order to do that?
Or grabbing the different water pressure.
The different water, yes, the longer the pressure of water. So you told me there were two reasons why these volumes were increasing. One was that the water was vaporizing, the other was the air was expanding. And we just want the water vapor part, we don't want the air part. We want to just measure the air part separately so we can subtract that out from all of these and get just the water vapor part of all of these. So how can we get just the air pressure without any water vapor?
You have to use when you have to use the water vapor, the change in enthalpy. Like isolate the change in enthalpy, but not like the vapor pressure and the volume.
Well, we need to calculate the change in enthalpy. We don't know that until the end. So we have to do that by getting just the water vapor pressure. So the total pressure in there, we're going to assume that's the same as the pressure outside, the atmospheric pressure. So we have to subtract, we're going to find out the air pressure and subtract that from the barometric pressure to get the water vapor pressure. And you think the vapor pressure of water is very high at this temperature? No. So what we have in there now is pretty much just the
The
air.
minimum, yeah.
Okay.
There's no vapor pressure left.
That's what we're going to assume. So if we assume that that's only air, then we're going to convert that volume to moles, convert it to a pressure, and subtract that pressure from the total pressure to figure out how much is left as the water vapor pressure. And that's what we use
And that's
for
why
enthalpy
we-
of vaporization.
Okay, so basically it isolates the change in enthalpy so we can use it.
Not the change in enthalpy, it isolates the water vapor pressure, so we can use that
So we can use that to
to
find it.
calculate the change in enthalpy.
Okay.
Okay. Good. Get a check mark.
Thank you.
Welcome. Here's another example from a different experiment. Students measure electrochemical cell potentials and use them to calculate half-cell potentials. Then they set up experiments to show that, for example, since copper has a higher reduction potential than lead, it follows that metallic lead will reduce copper ions in solution to metallic copper.
Waiting for you.
Yeah. Of all the combinations of copper, lead, and zinc that the students try, one has an interesting twist. Few students would notice anything different, and few of those would try to explain the observation, even though they have the background to do so. Explain to the instructor is the perfect instrument to focus their attention on the red and white stripes that form on the lead strip immersed in copper sulfate solution. Watch two students of different ability tackle this problem, and note too how deeper learning is encouraged by the one-on-one format.
The lead, when it is placed in the copper sulfate, is dissolving and giving off electrons.
Yes.
So then they reduce the copper ions, forming copper solid,
Yes.
which deposits onto the white strip.
And what color is the copper solid?
It's like a brown.
Ah, so you see that on there?
Yeah.
Yes. But you know, that looks like a white solid. Doesn't look like it's just the lead underneath it. So what do you think that white solid is?
The white solid?
Yeah. What other products would you get from that reaction?
You would get zinc ions. Oh,
You
and
mean lead ions.
I mean that's what I meant, lead ions, yes.
Okay. And what else is in the solution?
Sulfate?
Sulfate.
Yes.
Okay. So if you have lead ions and sulfate ions, are they going to be soluble or insoluble?
Insoluble.
That's right. Lead sulfate is insoluble, and that's the white solid. The other things that you make, the salts, are soluble, so you don't see that striping like that.
Okay.
And the copper sulfate is being reduced
Yes.
and lead is being oxidized,
Yes.
right? Okay, so the copper, and that's what when lead is being placed in the bases, the lead is being oxidized. It's releasing. I mean, it's gaining ions. I mean, it's gaining electrons, right?
It's losing the electrons.
It's losing the
when
electrons.
It's oxidized.
Okay, it's losing the electrons, and the copper is being reduced, so it's gaining electrons. So the solution has little brownish red color stripes or whatever it is.
Yeah, what's the brownish red?
Lead.
No,
It's not.
no, this is the lead right here.
Lead sulfate.
Lead sulfate's not that color.
It's not. Okay.
No.
So is it copper?
It's copper.
It is copper.
Doesn't it kind of look like copper?
Yeah, but it's dark.
Yeah.
So it's just because it's because it's oxidized.
No,
No, because it's reduced.
It's reduced, but it's probably because it's a thin layer and it's deposited along with something else.
Okay, so that's the color. Copper.
That's the color of the copper, but there's also something else in there. What are the white stripes?
So lead.
Lead? Well, lead looks like this.
Isn't that what it is?
No, no, it's something on top of the lead. It's not that silvery color. It's white.
It's white. Is it sulfate?
Sulfate is a compound?
Yeah.
No, sulfate is just an anion.
So it's copper sulfate.
Copper sulfate is the blue solution. It's soluble.
And so it's a lead sulfate?
Well, but sulfate's an anion. Is the lead a cation?
Yeah.
Why?
Because it forms, it's a plus.
It got oxidized in the reaction. But lead sulfate, would it be soluble or insoluble?
Lead sulfate's insoluble.
Insoluble, right, and that's why it deposits on the electrode. Whereas in the other reactions you did, you didn't have that because the salts remained soluble. Good.
So what about this one? It forms a silvery color thing.
Yeah, that's in the lead solution.
No, it's
lead
yeah, it's a lead
nitrate
solution.
yeah.
It's a zinc.
Yeah, that's actually lead metal forming. But when you get a very thin layer, it doesn't have the same properties as the bulk metal, so it doesn't have that same color.
Okay.
My students do most experiments without partners, so nobody can slide through without developing lab technique. But students who prefer to collaborate in pairs on explanations are allowed to do so, as we see here. So what's happening in the solution?
The lead is donating electrons to the copper, and the copper is sticking on the lead as it is accepting electrons.
And what color is that?
The red.
Red. So the copper is going from what oxidation state to what oxidation state?
0 to 2.
0 to 2. And the red is copper plus 2?
Plus 2 to 0.
Plus 2 to 0.
Yes.
Okay.
Solid.
Yes, and the red
And
is
the white is the
solid.
SO4 2 minus.
Well, anions can't be solids. Solids have to be neutral.
But it,
So if the copper is being reduced, what's being oxidized?
the lead.
From what to what?
From 0 to 2 plus.
0 to plus 2. So we have lead plus 2 forming, and there's sulfate ions in solution. So that could make lead sulfate. Would that be soluble or insoluble? You remember the solubility rules?
Insoluble.
Insoluble. So that's what the white stripes are, is insoluble lead sulfate. See, in the other one you have there, you're making, what's that, you're making,
Zinc
that's the
and
zinc, you're making zinc nitrate as a salt. And that would be soluble, so you're not, all you're seeing is the metal on that one. You're seeing the stripes of the metal in the salt, because the salt is soluble in that one.
Good job, Danielle.
Good job, Tiffany.
Everybody now! We start at the anode. Electrons are lost there and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where? Where?